On the scale of galaxies like our Milky Way, there would still be significant clumps of mass forming disk-like structures, and these disks would continue to spin, with star formation still taking place within them. However, without dark matter, these galaxies would differ in two major ways from what we observe today. In a universe lacking dark matter, galaxies would lose most of the gas needed to create new stars right after their first big burst of star formation. Sure, some gas could trickle in from minor mergers or the surrounding intergalactic medium, but they'd have far less raw material for making new stars compared to the galaxies we see now. Spiral galaxies without dark matter would rotate more like our solar system does, inner objects zipping around the center much faster than those farther out. The fact that most galaxies we observe have flat rotation curves, where outer regions move at speeds similar to inner ones, is another clue pointing to dark matter's presence in our universe. On larger cosmic scales, the structure would be much sparser. Without dark matter, there's no unseen framework holding together the vast cosmic web. Instead, everything would rely solely on the pull of regular matter. Today, we have this intricate cosmic web, galaxies linked by threads tying together massive clusters. But without dark matter, you'd just get scattered pockets of mid-sized galaxies. Some would still clump together, no doubt, but far fewer than we see now. The universe's large-scale layout would look starkly different by every measurable standard, from faint and strong gravitational lensing signals to galaxy group collisions, and the universe's power spectrum. And those tiniest galaxies, the ones with just hundreds or thousands of stars, they wouldn't stand a chance of existing at all. Back in 1989, astronomers spotted a colossal structure 200 million light years from the Milky Way, dubbed the CFA2 Great Wall. Stretching 500 million light years long, it was the first megastructure of filament-like galaxy clusters humanity had ever detected in the universe's endless expanse. Time marched on and tech got better, opening new windows for observation. At the dawn of the 21st century, in 2003, scientists unveiled the Sloan Great Wall, sitting over 1 billion light years away and spanning 1.37 billion light years in length. For a while, it reigned as the biggest known structure in the universe, until 2012, when a massive quasar group, sprawling across 4 billion light years, stole the spotlight. But that quasar group's time at the top was short-lived. In 2013, it got knocked off the podium by the Hercules Corona Borealis Great Wall, discovered through mapping gamma-ray bursts. These bursts are blindingly bright explosions from distant, massive stars, the most powerful flashes in the cosmos. A typical burst releases more energy in under a tenth of a second than the sun will in its entire lifetime. Gamma-ray bursts are rare, happening once every few million years in a typical galaxy. The stars behind these blasts are huge, so the stuff needed to form them has to be abundant. That makes these bursts handy for checking if there's a galaxy, or something even bigger, in a given direction. Before 2012, astronomers had been collecting these bursts across the sky, piecing together a map where they noticed something odd. 19 gamma-ray bursts showed strikingly similar redshifts and were clustered close together, hinting at a massive group of galaxies and matter in that region. This megastructure sits about 10 billion light-years from us, in the constellations Hercules and Corona Borealis, hence its name. That's not entirely accurate, though, since it's way bigger than both constellations combined. It also spills into Boötis and Gemini, and it's more circular than elongated. Still, the media latched onto Hercules Corona Borealis Great Wall, and it stuck. This Great Wall stretches about 10 billion light-years across. People often ask us to break that down into kilometers for easier grasping, but that's like measuring the trek from Vladivostok to Sydney in millimeters, except here, the number's even wilder. For perspective, the Milky Way, our home galaxy, is just 100,000 light years wide. The distance to Andromeda, which we're on a collision course with, is a mere 2.5 million light years. Now stack that against 10 billion. Pretty mind-blowing, right? Add in the structure's width of 7.2 billion light years and thickness of nearly 1 billion light years, and you've got dimensions so outrageous they're hard to wrap your head around. The Hercules Corona Borealis Great Wall takes up 10% of the observable universe's area. It's packed with billions of galaxies, all knit together by gravity. Here's the kicker, though, you probably caught it too. It's 10 billion years old. That means it existed less than 4 billion years after the Big Bang. That's where things get messy in the science world. But first, let's unpack this redshift business. It's worth digging into either to learn something new or brush up if you're already in the know. It'll come in handy later, trust me. There's this thing called the Doppler effect. You've likely heard of it. It's straightforward. If a wave emitting source moves toward you, the waves compress and you see a shorter wavelength. If it's moving away, the waves stretch and the wavelength grows. For light, say from a star, if it's heading away from Earth, the wavelength stretches and the light looks redder. If it's coming closer, it shifts blue. Blue light's wavelength is about half that of red, but since blue and bright stars dazzle so much, our eyes often register them as white. This isn't just for light or space. Sound and other waves follow the same rule. Still, watching it play out across a star-strewn universe is way more captivating. That's what Christian Doppler thought, too, when he published his 1842 paper on the colored light of binary stars and others in the sky. A bit later, in 1848, French physicist Hippolyte Fizeau tied this to shifts in star spectra. It's simple. The more a spectrum shifts red, the faster the object's moving away from us. One side of a galaxy's light might redshift, the other blue shift, meaning it's spinning. Far-off galaxies show bigger shifts than nearby ones, growing with distance. So, the farther a galaxy, the quicker it's receding. Redshift ties into relativity and the idea of expanding space. That shift comes from both space stretching and galaxies' own motion. Here's the easy version. As light travels from its source to us, space expands, stretching the light's wavelength along the way. If space doubles in size, the wavelength doubles too. That's the gist. Pretty basic, really. We could dive deeper. It's a huge topic, but that's not our focus right now. The Hercules Corona Borealis Great Wall is calling. What's off about it? It clashes with something called the cosmological principle, which says the universe should be roughly uniform. Any random quirks in structure or mass between cosmic objects should be tiny. That uniformity should kick in at scales of 250 to 300 million light years, called the end of greatness. Structure should max out at about 1.2 billion light years, assuming matter spread evenly from the Big Bang. But this Great Wall, 8 times that limit, throws the whole principle into question. Its discovery got labeled too big to exist. Plus, at 10 billion light years away, we're seeing it as it was 10 billion years ago, formed just 3.8 billion years post-Big Bang. That's too short a window for something 10 billion light years wide to take shape. It seems to defy the universe's evolutionary model, which doesn't allow for such massive, complex structures that early. Even Istvan Horvath, who studied it, admits he's stumped on how it came together so fast. This find hints the universe might be older than we think, shaking the Big Bang theory that's already been tossed around like a dinghy in a Pacific storm. Could spotting such a giant be a mistake? Doubtful, though hypothetically possible. Some astronomers question redshift theory, floating ideas that light reddens over vast distances through thin intergalactic gas, losing short wavelengths without spectral line shifting. But redshift, as we know it, hinges on that shift. Maybe light loses energy on its endless trek, stretching its waves, yet no one's proven how or where that energy goes. Quasars show bigger redshifts the farther they are, backing the standard view. Still, there's this thing called statistical significance, and for the Hercules Corona Borealis Great Wall, it's murky. Most likely, it doesn't outright break cosmic uniformity. For now, its existence, along with other megastructures, remains a puzzle for cosmologists. Info on it is scarce, even in English sources, but we've rounded up the juiciest bits for you. So, don't slack off. Give us a like, drop a comment. We need your support. Catch you at the next cosmic meetup. Lately, buzz has been growing around the notion that our universe, and us with it, might live inside a black hole. These mysterious beasts warp space and time so wildly they swap places. Crazy as it sounds, it's not as far-fetched as you'd think. Let's unpack it, but first tune your brain to deep think mode. A black hole's defining trait is its event horizon, a boundary where the story differs drastically depending on whether you're outside or inside. Outside, any object feels its gravitational tug as space bends around it. Escaping that grip seems impossible, but it's not always. If something moves fast enough and accelerates just right, it can slip free. Inside the horizon, though, it's a different tale. Cross it, and you're doomed to hit the central singularity almost instantly, adding to the black hole's mass. Space-time bends so sharply inside that a falling object reaches that core in seconds. To an outsider, the black hole looks like it's growing, piling on mass over time. So, where does our universe fit in? Tally up all the measurable matter and radiation we can see: baryonic matter, protons, neutrons, electrons, elusive neutrinos, dark matter, a mass champ we can't directly catch, photons carrying energy from every cosmic spark, and gravitational waves rippling from moving masses. The farthest edge our tools can peek at stretches about 46 billion light years in every direction. Crunch those numbers, and you get the universe's equivalent mass. Here's a wild thought. What if all that got squeezed into one point? Same thing as compressing any big chunk of mass or energy, a black hole would form. In gravity theory, if that pile isn't electrically charged or spinning, its total mass alone sets the black hole's size, known as the Schwarzschild radius. Here's the kicker. A black hole with the mass of all observable matter matches our universe's observable size almost spot on. That's a stunning coincidence, sparking the question, could our universe be inside a black hole? That's just the start. Things get weirder. In the mid-1960s, a game-changer hit. A uniform bath of low-energy radiation was found blanketing the sky. It's the same temperature everywhere, 2.725 Kelvin, just above absolute zero, with a near-perfect black-body spectrum, like it came from a hot source. It's consistent to 1 part in 30,000 Celsius, no matter where you look. This cosmic microwave background is proof our universe is expanding and cooling from a hotter, denser past. The farther back, the smaller and tighter it gets. Extrapolate that to a singularity, and it mirrors a black hole's core: extreme density, temperature, and energy-breaking physics as we know it. Imagine standing just outside a black hole's event horizon, stretching to infinity. Distance runs from the Schwarzschild radius outward. Inside, from the horizon to the singularity, it flips, from that radius to zero. That flip matters big time. Compare space outside a black hole, radius to infinity, with inside, radius to zero, and they're mathematically identical at every point. A black hole's interior mirrors its exterior. Two breakthroughs shape this view: cosmic inflation and dark energy. Inflation says the universe didn't spring from a singularity, but a rapid exponential expansion phase before the hot Big Bang, driven by some field fueling space itself. Dark energy, meanwhile, kicks in as the universe thins out, pushing distant galaxies away faster over time, like energy baked into space. Could dark energy stem from a black hole's spatial quirks? Is there a link between it and inflation? Black holes might hold clues. They grow by gobbling matter and shrink via Hawking radiation. As their horizons shift, could that tweak the energy of space inside for someone watching from within? Does cosmic inflation mark our universe's birth from a supermassive black hole? Could dark energy tie back to them too? Might every black hole in our universe spawn its own mini-universe inside? These ideas have floated around for decades without solid proof. Still, models abound, drawing in folks studying black holes, thermodynamics, entropy, relativity, and the universe's start and finish. No theory's nailed it yet. Roger Penrose's cyclic cosmology comes close, spotting low variance Hawking points in the microwave background, hinting at something. There's a thread connecting black holes in our universe's birth, maybe to a massive one from a prior cosmos. Each black hole here could birth another. We don't know if we're inside one, but the possibility's too tantalizing to dismiss. True or not, black holes are keys to unlocking cosmic riddles: Big Bang, inflation, dark energy, and all. Black holes stand out as some of the most extraordinary entities in the cosmos, packing enormous mass into a tiny sliver of space and bending the fabric of reality so intensely that anything crossing a certain threshold can never break free, not even if it's moving at the ultimate cosmic speed, the speed of light. It seems that across every galaxy like our Milky Way, trillions of these enigmatic objects are scattered, with the biggest ones tipping the scales, at billions of times the sun's mass. Yet when you ponder how all these black holes came to be, it's reasonable to conclude they started from ordinary matter, the stuff made of atoms we're familiar with. None of them appear to have sprung from dark matter, even though dark matter outweighs regular matter in the universe by a hefty 5-to-1 ratio. If black holes are born from gravity's pull, and dark matter feels that same tug, what's stopping it from forming black holes too? Today, we're diving into a cosmic tale. Can black holes be made of dark matter? And if not, why not? In our current understanding of the universe, only a handful of ways exist for black holes to come into being. Perhaps the most common route is the collapse of a massive star's core. Stars fend off gravitational collapse, with the energy churned out by nuclear fusion in their hearts, where outward radiation pressure balances the inward crush of gravity. When a star's core runs out of fuel to burn, that radiation pressure dips, and the core starts shrinking under its own weight. As it compresses, the core heats up to temperatures that defy imagination for anyone watching from the sidelines. The hotter it gets, the more likely the core can ignite even heavier elements as fuel. Once those run dry, if the core's massive enough, it caves in during a Type II supernova explosion, forming a black hole by squeezing a huge mass into a minuscule space. If it's not quite heavy enough, a neutron star emerges instead. Another path to a black hole is the smash-up of two neutron stars, if their combined mass crosses a critical limit after merging. Then there's direct collapse, where a lone, hefty star grows so dense that light can't escape a certain region anymore. Once that tipping point hits, an event horizon forms, and anything crossing it is locked in, doomed not just to stay but to quickly pile onto the growing mass and size of the newborn black hole. In a flash, it can swallow all the mass of whatever it came from, birthing a full-fledged black hole. Sure, there might be wilder, more exotic ways for black holes to pop up, but these are thought to account for the vast majority we can spot in the observable universe. You might have noticed a pattern here. All these methods lean on ordinary matter, atoms and their building blocks. That's even more striking when you consider some numbers. Ordinary matter makes up just a sixth of the universe's total mass, while dark matter claims the other 5/6. Both types feel gravity's pull the same way, bowing to Newton's and Einstein's laws alike. In any spot brimming with regular matter, like a Milky Way-style galaxy, dark matter's there too, outnumbering it at least 5 to 1. So, why does regular matter churn out black holes so well while dark matter doesn't? The answer isn't in gravity itself, but in other forces, like friction and collisions tied to electromagnetic interactions. Regular matter deals with these, dark matter doesn't. When a galaxy forms, dark and regular matter start out mixed in that 5 to 1 split, a trend holding across the cosmos. Both, tugged by gravity, drift toward the galaxy's gravitational center, picking up speed as they go. Here's where it gets juicy. Dark matter sails through a galaxy with no friction, no heating, no dance with electromagnetic radiation, and no way to swap energy or momentum with other particles inside. It lingers on slow, wide orbits with lots of angular momentum, maybe taking 1 billion years to trace a single ellipse. Regular matter, though, has all the tricks dark matter lacks. It bumps into other bits of baryonic stuff, trading energy and momentum. Collisions sap kinetic energy and angular momentum. It heats up from friction, reacting to radiation. Together, these effects draw a sharp line. Regular matter sheds angular momentum and sinks toward the galaxy's core, while dark matter stays spread out, forming a diffuse halo around it. Regular matter clumps into tight, dense pockets. Dark matter forms rare, sprawling clusters. Without a way to ditch angular momentum, dark matter can't even sniff the density needed to forge an event horizon, and thus a black hole. No dark matter stars eggs, so there's no core collapse for it. No regions ever pack enough dark matter to trap light back onto itself, ruling out direct collapse. And there are no dense stellar remnants or objects made of dark matter to crash together and spark a black hole. Every trick regular matter uses to collapse into a black hole falls flat for dark matter. Now it's clear. When a black hole forms from regular matter, dark matter particles can't cross the event horizon to bulk it up. In that sense, dark matter's no different from any other matter or radiation cross the horizon, and it's a one-way ticket to the central singularity, boosting the black hole's mass. But given regular matter's clumpy nature versus dark matter's spread-out vibe, there's no real way even 1% of a black hole's mass could come from dark matter. Based on what we know, there's just one shot at a dark matter black hole. If the very early universe had huge density ripples that collapsed fast, forming black holes before stars ever showed up, that could spawn primordial black holes independent of stars. Here, mass is all that counts. Since it's pure gravitational physics and how structure forms in an expanding universe, you can figure out the extra density needed for a primordial black hole. If a patch starts 68% denser than average, regardless of the baseline, it'll collapse into one. Our universe kicked off with the spectrum of fluctuations, seeding the structures we see everywhere, etched in the cosmic microwave background's temperature quirks, its correlation functions, and the power spectrum of large-scale structure. In science, asking the right questions matters, resisting the urge to twist facts into wishful thinking. Instead of dreaming up ways around limits and asking, could I believe this? We should stick to the evidence with minimal assumptions. What's the universe telling us, and why can we trust it? That's the heart of science. Without evidence backing a hypothesis, it's reckless to call it true. Given what we know about dark matter, we shouldn't expect black holes, now or ever, to be mostly or wholly dark matter. No stars, supernovae, remnants, or direct collapse scenarios point to dark matter black holes, and it can't get dense enough post-universe start to pull it off. Unless we lean on new, unseen physics to craft a batch of primordial dark matter. Black holes, we can confidently say regular matter, not dark, drives the black holes we see in our cherished universe. Don't forget to thumbs up this video and subscribe. Out there in Virgo, 29 million light-years from Earth, sits the Sombrero Galaxy. Shift to Perseus, 220 million light-years away, and you'll find the compact lenticular galaxy NGC 1277. Push farther to Cetus, and there's the supergiant elliptical Holmberg 15A. These galaxies dot different corners of the cosmos, varying in shape, type, and size, but they share one thing, a colossal supermassive black hole at their core. Sombrero's clocks in at 1 billion solar masses, NGC 1277's at 17 billion, and Holmberg 15A's ranges up to 10 billion, depending on who's measuring. We've cataloged the heftiest black holes we've found, mostly parked at galaxy centers. We're just starting to pen our saga of cosmic conquest. We know a lot, but so much more awaits discovery. We get how supermassive black holes work, but their origins? That's fuzzier. One of the oldest ones formed less than 1 billion years after the Big Bang, clashing with some theories. How could such massive beasts emerge so early? Plenty of ideas try to explain it, each with its merits and flaws. Today, we'll unpack one of the wildest and most gripping, a hypothetical tale depending on your angle. Let's roll through it step by step. Normally, this'd be prime ad break territory, but with no decent offers, we'll shamelessly plug our channel. Stick around, it's about to get good. So slap that like button now so you don't forget, and hit the bell to catch all our space vids. That was our little ad detour. Now back to it. To grasp one take on supermassive black hole origins, we're zipping back to the early universe, when the first stars, dubbed Population 3, flickered to life. These were the cosmic trailblazers, great-grandmas to stars like our sun, made purely of hydrogen and helium since heavier stuff hadn't cooked yet. They kick-started the element factory, growing massive and burning out in about 1 million years via hypernova blasts, their cores collapsing into hefty black holes. None survived to today, so they're theoretical. But these ancient stars are our focus. What if not all collapsed post-hypernova, and some were so huge they turned into quasi-stars? Don't mix these up with quasars, those blazing radio beacons powered by supermassive black holes. Quasi-stars look like stars, just way bigger than any you've heard of. They dwarf giants, supergiants, even hypergiants. UY Scuti or Stevenson, 2 after 18? Tiny toys next to a quasi-star. These beasts boast a 10 billion kilometer diameter, over 3 times Stevenson 218's, and a mass at least 1,000 suns, while R136A1, today's heaviest known star, sits at 315 solar masses. Their brightness? At least 100,000 suns. Picture a star filling nearly our whole solar system, stretching past Pluto's orbit, with the mass of a small globular cluster and shining like a mini galaxy. That's a quasi-star. Their temperature's less dazzling, around 10,000 Kelvin, still almost double the sun's, but size isn't what sets them apart. Regular stars run on nuclear fusion in their cores. Quasi-stars, they've got a black hole inside instead. Fair warning, quasi-stars are pure theory. Not long ago, scientists floated them as possible ancestors to supermassive black holes, probing what it'd take to form them. From clouds of hydrogen and helium, protostars emerge, clumsy, growing blobs rounding out as they gobble up more stuff, not yet hot enough for core fusion. As heat and pressure climb, gravity squeezes the gas tighter. If one of these chunky protostars cores, collapses into a black hole, it starts slurping up the surrounding gas, radiating heat to power the star. You might think that collapse would blast away the outer layers, end of story. But quasi-stars are so massive, those layers stick around. What's left is a stunner, a sizzling stellar shell with a monster inside, fueling it for about 7 million years. To keep going, that black hole chows down on 14% of a solar mass yearly. When the star dies, only the black hole remains, primed to balloon into a supermassive giant, billions of solar masses strong, anchoring a future galaxy. Quasi-stars stay hypothetical because population 3 stars are too. Born in the pristine aftermath of cosmic creation, built from the lightest elements, they swelled to sizes we can barely fathom. Such giants don't last long, making evidence of them elusive, maybe impossible, to find. Were protostars massive enough for quasi-stars? Today's data suggests that with less than 1 million solar masses, they'd likely just become supermassive stars, not quasi-stars. Our grasp of star formation and gas collapse is shaky. Direct collapse still floats as a way to explain supermassive black holes powering distant quasars 1 trillion times brighter than the sun, maybe from the biggest stars we haven't seen yet. Usually vids about huge objects toss in a "what if it replaced the sun" comparison. For fun, let's mix it up. Imagine a quasi-star barging into our solar system from Neptune's turf. What then? We'd spot it way sooner than you'd guess, long before it crashed our system. The closer it got, the brighter Earth's skies would blaze. But it's not just extra daylight. Once it breaches the solar system, planets, asteroids, everything would likely get flung off their paths, and we'd feel it. Earth would face epic meteor showers, thousands of rocks piercing our atmosphere and slamming the surface. A quasi-star would plow through, gobbling Neptune, then our gas giants. Its proximity would roast Earth fast, hitting 260 degrees Celsius. The atmosphere turns to steam and CO2. At 760 degrees Celsius, sulfur dioxide joins in. The heat keeps climbing until Earth's crust and mantle vaporize, and the whole planet gets swallowed. Hit that subscribe button if you're as space obsessed as us, and toss a like if this vid clicked, means a ton. See you next time.